Okay, today we're going to start the chapter 2, which is about electrostatic. Okay, so before we start to introduce the electrostatic field, first let's review a little bit about Coulomb's law. So do you remember what is Coulomb's law? Um, So it describes the force between two charges. Let's say if you have a charge Q here, and then you have another test charge capital Q here, which has a distance of R between Q and Q. So these two charges are point charges, which means these two charges, they don't have volume, um, but they have charge. So it's ideal case. In this case, the force between those two charges could be described by Coulomb's law, which is shown here. F equals to 1 over 4 pi epsilon 0 times Q1, Q2 over R squared. And the direction of the force is in the direction of the vector between Q1 and Q2. And of course, if the two charges are all positive, then they repel each other. The force will be repulsive force in the direction of repulsive. And the same thing for two negative charges. If the two charges are all negative, it's also repelling force. However, if the charges are positive and negative charges, then they attract each other. In the direction of the force will be in the opposite direction. And here, there's a constant, which is epsilon 0. It's the permittivity of free space. In SI unit, the force is in newtons, distance is in meters, and the charge is in coulombs, and epsilon is in this value. It's a very small value. And this R here, it could be described by R, vector R subtracted by vector R prime. Let's say if Q is in the position R, which is shown here, and another Q is in the position R prime, then their displacement vector will be this R, the R subtracted by R prime. Okay, so that's the force between two charges, or between a charge, a point charge, and a test charge. So if there are more than one charges, and then if you put a test charge in the system, you can calculate the net force of on this test charge and generated by all the charges in the system. For example, now you have a lot of point charges like Q1, Q2, Q3 until Qi. You have I point charges here. And now if you put, let's say, a charge Q at the position P, then you can calculate the force between Q1 and test charge Q, which is from the Coulombic function. And you can also calculate the force between Q, the capital Q, and Q2, which is based on the Coulombic function. And for each point charge Q1, Q2 until Qi, it generates a force on the test charge capital Q, and the force is F1, F2, until Fi. And we know how to do a net force. You can calculate a net force by a vector sum of all the forces performed on the object. Now, if you have F1 performed on the test charge Q, F2 performed on test charge Q until Fn performed on the test charge Q, then you can sum up all the F1, F2 until Fi, all the forces from the source charges. Of course, it's a vector sum. And for F1, it's 1 over 4 pi epsilon Q1 Q over R1 squared in the direction of R1 head. And for F2, it's similar. The difference is the Q2 and R2. So for all the charges, you can calculate the force on each of the source charge. And then if you do a sum, finally you will calculate the net force in this form. The test charge Q over 4 pi epsilon 0, it's a constant, times Q1 over R1 squared in the R1 direction, Q2 over R2 squared in the R2 direction until Qi. And then we can take this part out and we can write it into E, which is field, the electric field. So that is the electric field generated by all the source charges. Then the force could be written in F equals to test charge times the force field, the electric field, electrostatic field, E. And E, of course, equals to 1 over 4 pi epsilon, then the sum of Qi over Ri squared in Ri direction. So this is the electric field. And the electric field is from, of course, Coulombic equation. For a single charge, it is easy. For a single charge, the electric field is generated by only one charge, but for multiple charges, you can use a sum of all the electric field generated by each source charges. And the sum, of course, is a vector sum. So E is called electric field. And if you want to calculate the electric field at point P, you need to calculate the electric field generated by Q1, which is in this direction, Q2, which is in this direction, Q3 until Qi, and then you do the sum. Then you get the electric field at point P. Okay, that's the concept of electric field. Now let's do an example. Find electric field at a distance z above midpoint between two equal charges Q, a distance d apart. Okay, so the figure is here. Now you have a point, a test point P here. It's z above Q and Q. So the distance between the two charges Q and Q are D. So let's take the coordinates in this way. Q and Q are on the x-axis and the point P is in the y-axis. So the distance between Q to the origin will be Q over 2. The distance between Z to the origin will be Z. So first, let's draw the picture in this way. Let's calculate E1 and then calculate E2 and the sum of E1 and E2 will be the E generated by the two charges. So let's first calculate E1. How to calculate E1? Let's use Coulombic equation, which is this Q over, okay, let's show it here. It's Q over 4 pi epsilon R squared. R is shown here. This is R. This is also R. Um, so that's E1. But if you want to calculate EZ, you need to calculate, let's say, the let's say Z component of E1, which is E1 times cosine theta. The same thing for E2. It's E2 times cosine theta. Actually, E1 and E2, they're in the same magnitude. So you have 2 times E1 or EQ. They're in the same magnitude. Then times cosine theta. That will be your EZ. So here, the distance R could be calculated in this way. R equals to the square root of Z squared plus D over 2 squared. Then cosine theta equals to Z over R. So if you take R and cosine theta into this equation, you will have E equals to this equation. And the direction is in Z direction. It's going up. And when Z is much, much greater than D, or if Z is in a very long distance compared to the distance between Q and Q, then you're so far away as it looks like a single charge to Q. So you will see if Z is big enough, the field source, this equation will degenerate it into 1 over 4 pi epsilon 2q Z squared in Z direction. So that means if Z is very long, then the two charges performs like a single charge. Okay, so that's Coulombic equation and electric field for discrete point charges. So if you have multiple charges, they're discrete charges. But in many cases, some charges are not discrete. It's continuous charge, like continuous charge distribution in, let's say, a volume, or in a line charge, or in a surface, and in a volume charge. So in this case, if the charge is not a discrete point charges, instead the charge is in a distribution which is continuously over some region, then the sum of the electric field becomes integral. Now let's see the equation of sum. So if it's for point charges or discrete charges, the field could be written in the sum of electric field for point charges. But if it's continuous charge distribution, then the sum becomes integral. So that's the definition of integral, right? Integral means sum, but it's a sum of continuous or infinitesimal values. So in this example, it's sum of very small point charges. You can consider the continuous charge distribution to be infinitesimal charge points. So the sum of infinitesimal point charges actually is an integral of a charge distribution. So if the charge is um, distributed along a line, then with charge per unit length lambda, you will have dq equals to lambda dl prime. Dl prime is an element of length along the line. If the charge is smeared over a surface, then in this example, so this is the charge over a surface, then what you can do is you can describe an infinitesimal piece of or patch of the surface to be dA prime, and the surface charge density, um, let's say, is sigma, then dq equals to sigma times dA prime. And if the charge is in volume, then you can consider infinitesimal volume, which is dt prime, and the charge density, let's say, is rho, then dq equals to rho dt prime. Then the electric field of a line charge becomes 1 over 4 pi epsilon 0, the integral of lambda r prime, because now the lambda, or the charge per unit length, is a function of your line. For example, this is a line. The charge is distributed along this line. Then the charge density along a line, or charge per length unit along the line, is a function of this line, or a function of the position. Then dl prime. And the direction, of course, is in the r direction. So if it's a surface charge, then the difference is it becomes a surface integral, and here it's a sigma. Sigma is a surface charge density. It's a function of r prime. Direction is still in the r hat direction, which is the connection between your infinitesimal surface patch and your test charge position, times dA prime. dA prime is the infinitesimal surface. And for volume charge, it becomes rho. Rho is volume density of charge times dt prime. So dt prime is the infinitesimal volume. Okay, so that's the ways of calculating continuous charge distribution for line distribution, surface distribution, and volume distribution. Now, let's do another example. This example is about the line distribution calculation for continuous charge distribution. Find the electric field of a distance z here above the midpoint of a straight line segment of length 2L, which carries a uniform line charge lambda. Okay, so it's similar to the previous case. In previous case, we're going to calculate the field generated by two charges, that's 2 point charges. But in this case, we're going to calculate not 2 point charges, but many point charges. It's infinitesimal small point charges distributed on a line, so which becomes integral instead of a sum. Okay, so what we can do is we can use this, let's say, electric field calculation from derived from the Coulombic equation, which is shown here. This is for the line distribution of charges. So what we can do is we need to use this equation. So we need to know, so first of all, 4 pi epsilon, it's constant. So we need to know the lambda, which is the, let's say, linear density of the charge. And then we need to know the r squared, which is the distance between your dl prime and your test point P. And we need to know the direction between your dl prime and your test position. And then we need to have this dl prime and do the integral. Okay, then first let's see what is r. So for r, which is the position for the test point, it's a z. Let's say if this is z, then it's z in z direction, of course. So z in z direction. Now, the important thing is, of course, this one, the r, which describes the direction and distance between P and dl. Oh, sorry, dl prime. Here, dl prime equals to dx. The r prime here is x in x direction. So this is the, let's say from here to there, this is r prime. This is r. R is z in z direction. R prime is x in x direction. And this r equals to r subtracted by r prime. This is what we have learned in the chapter 1. So if you know r, you know r prime, then it could be described in this way. So r is z in z direction, r prime is x in x direction. So this is the direction of this r, the displacement direction. And the distance or the magnitude of this r, which is the distance between your dl prime and your point charge, it's square root of z squared plus x squared. That's easy to be calculated. And the unit vector r equals to r over r, which is shown here. Now let's take all these things into your equation shown here. That's your equation. Then if you plug all these things in, you will get the equation shown here. 1 over 4 pi epsilon 0, it's constant. You can put it out. And the integral is from, let's say, negative L to L. This is negative L, this is L. You need to do the integral from here to there. And then lambda, lambda over z squared plus x squared. So this is r squared as shown here. Here you need r squared. So here is your r squared. And this is the r direction. And then dl prime becomes dx. That's easy. And then you will have two terms. So the first term is, let's say, the term. Okay, let me write it down. Let's say the first term becomes 0. put this figure down. Let's move it down. Oh, what happened? We need to move them off. Maybe we need to group them first. And then let's move. Oh, what happened? Okay, I can't move it down. So it's okay. It's okay. So we'll write it small. So you hopefully we can write it all. So it's lambda z squared plus x squared. So this is z squared plus x squared. This is square root of z squared plus x squared. So totally, if you combine them, it's 3/2. So it's a z squared plus x squared to the power 3/2, because this is power 1. This is square root means power of 1/2. So totally it's the power of 3/2. And the constant lambda is written here. So you can move it out actually. Let's move the lambda out. Then you can erase this lambda. And then you have z in z direction dx subtracted by the same thing, z squared plus x squared 3/2 x in x direction dx. Okay, so now you have two terms. You need to, if you're familiar with this calculation, then you will know z is, in this term, z can be considered as, of course, it's integral. Two integrals. So in this integral, z can be considered as a constant because it's integral for dx. But in this part, x is not, x cannot be considered as a constant. So you can look up your integral form or the useful integral tables to see how to do the integral in this form and this form. And then you will finally figure out, so in the first form, z is constant. Oh, it already written it in this way, so I don't have to write it. Okay, so look up your integral table. You will know this integral result in this equation, and the other integral result in this equation. So finally, you plug the upper limit and lower limit, which is L and negative L, you will get the final answer for this electric field. Okay, so if the point is very far from L, then E becomes 1/4 pi epsilon 0 to lambda L over V squared. And this equation looks like a point charge Q equals to 2 lambda L, because 2 lambda L, that's the charge of Q. So that means if your testing point is very far away from this line charge distribution, then the electric field looks like a point charge. Okay, That's all for today's class. So here it's another useful video which describes the continuous electric field. If you're interested, please watch this video. It might be helpful. Okay, that's all for today. Thank you.